Sound check. Can everybody hear me?
Oh.
Yep. All good. Okay, well, so welcome to the next lecture in S081, wherever you are. I hope that the folks on the West Coast or in Florida and Alabama do okay, given all the terrible circumstances there. The topic for today is virtual memory. In particular, we're going to talk about page tables. We'll return to this topic a few times. There will be multiple virtual memory lectures. And maybe just to start off and get our question and answer going again, I would like to ask you a little bit on what do you remember from about virtual memory from 004 maybe or 6033 if you've taken that. I'll tell you my own sort of view on virtual memory, which is, when I took it or first heard about it or learned about it as a student, I thought, it's pretty straightforward. Hard can it be? It's a table that maps virtual addresses to physical addresses. Maybe a little bit more complicated, but, not that complicated. And only when you start programming with it, I sort of really learned that virtual memory is tricky and fascinating and very powerful. And so hopefully in the next couple lectures and the next couple labs, you'll appreciate virtual memory from that perspective. But I'm going to ask you a couple people here that are online, what do you remember from about virtual memory from either 004 or 6033 if you've taken it? And again, I'm just going to call out some names and share your memories. How about Adela Yang?
Oh, sorry, what was the question?
What do you remember about virtual memory from maybe 004 or 6033 if you have taken that?
It uses like offset to save on like remembering virtual address to physical address mappings.
Mm-hmm. Okay. How about Abraham Scandera? Abram, are you online?
Yeah, my memory is that it uses, like it's a way of, one, protecting the physical hardware by kind of using your own representation of it. And then, yeah, you just have like some virtual address, things like, at least in 004, it's like 12 bits that maps some physical address that's usually, I think, 16 bits or 64 bits or something like that.
Okay. How about Vivek Pandit?
What I remember was you can have each process has a separate address space, and the memory management unit, or some other technique, can be used to map the virtual addresses of the address space of each of the processes to the physical address. And the virtual address, the lower bits are kind of the same, so that the mapping is in blocks, which helps with performance.
All right, good. Wesley Wu.
Yeah, I guess what I remember most is that virtual addressing allows us to protect the physical addresses from each process, and we can use some like clever manipulation so that the bits that correspond to the physical address can be used somehow in the virtual addresses as well.
And Wilson Spearman, or Spearman.
Yeah, I remember it's really fundamental to isolation because every process can basically pretend that it has its own set of memory to use.
Yeah, good. Well, so clearly, that's awesome. The sort of clear two themes here, correct? One is, there's some form of mapping, and that mapping is helpful in sort of achieving isolation. And this is exactly the reason we're talking about virtual memory, isolation. So what we'll see is that in the next, the next couple of lectures, and particularly when we start programming with virtual memory, really get an in-depth understanding of what its power is. And so to get a sense of that, this is the first lecture, and I'm mostly focusing on the mechanisms for virtual memory. And then later we can see how we can use these mechanisms to achieve, cool tricks. So the topic for today, or the agenda for today, the plan is sort of threefold. First, I'm going to talk about the address spaces, as some of you mentioned in your just briefly mentioned in response to this question. Then I'm going to talk about the paging hardware, and I'm going to focus, of course, on the paging hardware of the RISC-V. But basically, every processor, modern processor, has some form of paging hardware. And that's sort of if you will, the default mechanism for actually supporting virtual memory. And then the last part of the lecture is going to walk through some XV6 virtual memory code and layout of the kernel address space and user address spaces. So that's the main plan. Okay, so I guess as a number of you mentioned in the response to this question, one driving reason to have virtual memory is because you can use it to achieve isolation. And if you set up the page tables correctly and program them correctly, then you can in principle achieve strong isolation. And so let's just remind us again, what we want from isolation. Let's just say, our standard picture, we have some user applications, like the shell, cat, all the util things that you built in lab 1. And, we have the kernel, or, the kernel sitting below it, or the operating system sitting in kernel space. And, what we like to do is sort of have, boxes around these applications so that they can't really affect with each other. And similarly, we want them to be completely sort of independent of the kernel and the operating system, so that, like, if an application does something either accidentally bad or maliciously bad, that it doesn't really affect the operating system. And so that's our goal. And the particular aspect of the problem that we want to focus on today is the memory side of things. So we really want to focus on memory isolation. And by default, if we don't do anything, we don't really have memory isolation, right? Because if you think about it, there's going to be one, the RISC-V board that I showed you last week, it has like a memory, a bunch of DRAM chips. And in the DRAM chips, the code for these applications is stored. And so, for example, somewhere in the memory is the kernel, text and data, stack, everything. Somewhere in memory is the shell, if the shell is running. Somewhere in memory is the cat program. And so there's one sort of physical memory, starting from some address 0 to, some, big address, depending how much memory we actually have in our machine. And in that physical memory, all these programs must be present. Otherwise, the processor can't even execute their instructions. And so what the risk, clearly here is that, let's say, let's make it a little bit, simplistic, but let's say, the shell, sits from address 0 to address 200. Or 2000, from 1000 to 2000. And let's say, whatever cat has a programming error, it loads, in a register A0, let's say it loads 1000, the address basically corresponding to the start of the shell. And then, by accident, it executes the instruction, $7 A0. Right, which has the effect of basically it writes the value 7 to the address 1000, and so then it would be scribbling over basically the memory image that belongs to the shell, and so that would certainly not that certainly would break isolation and be quite undesirable. And so we want something that basically really separates these memories from the different programs from each other, so that things like that just cannot happen. So one way to do that is an idea that's typically called address spaces. And the basic idea is sort of straightforward. What we want to do is basically give every application, including the kernel, its own address space. And so we can think about this, like, for example, here's cat running. you know, it has an address space starting at 0, you know, to whatever, so maximum value. You know, there's the shell has an address space, its own address space, also starting at address 0, and you know, going to some value. You know, the kernel has its own address space. The OS has its own address space. And so one example, when cat, you know, refers to, really, we go back to our, you know, the example of the previous slide where we, you know, we did whatever, store 7 to, you know, A0. And let's say in A0, there's the value 1000. You know, if cat, you know, executes an instruction, it will write to the address 1000, but it's its own address 1000. It's not, you know, the address of the 1000 of the shell. So basically every program runs with its own address space, has its own value, and those address spaces are completely independent. You know, in this notion of there's different address spaces, cat doesn't really have an ability to even refer to an address that actually belongs to the shell. And so that's sort of the game that we're, the end goal that we'd like to achieve, because this is going to provide us with strong isolation, because, you know, and it's just not possible for cat to refer to any other memory that is not, you know, its own. And so our goal now is to basically sort of figure out how to multiplex, if you will, all these different address spaces on a single physical memory, because in the end, we only have a bunch of DRAM chips, where, you know, or RAM chips where the memory is located. And so, so that's our plan. Okay, yeah, Amir, you have a question, go ahead.
Yeah, so I'm wondering, in the configuration of the physical hardware, there's only so much space.
Yeah.
And in the virtual memory layout, there's also a max virtual address.
Mm-hmm.
By design, is the virtual address made to be small enough?
No,
that it...
no, not necessarily. You know, the virtual address space could be bigger than the physical memory. The physical memory could be bigger than the virtual address space. And we'll see in a second how that all can happen. And it's actually one of the, you know, cool parts about, as we will see with page tables, that's extremely flexible.
So is it possible that, like, the physical memory gets exhausted because so many processes use up all their virtual space?
Yeah, that's certainly possible. And we'll see in a second how. For example, you know, if you have a bunch of big applications that each have big page tables and they allocate a lot of memory, you know, at some point you're going to run out of memory.
I see. Thanks.
And so where does it show up in x86? Anybody? You sort of touched on it a little bit in the syscall lab that you're currently doing. Where are pages allocated? Or if you did the syscall lab and you finished it, you know, one part of the syscall lab correctly is printing how much free memory there is.
kalloc?
Yeah, kalloc. Right. So kalloc has a list of free pages. If that list of free pages is empty or runs out at some point, then, you know, kalloc is going to return a null pointer. And hopefully the operating system does something sensible, and that basically propagates back to the user application saying, like, well, you know, no more memory for you, or no more memory in total for nobody. Okay. And it's the job of the OS to handle those cases gracefully, where gracefully generally means, you know, propagating an error message to the user application. Okay, good. So how do we implement these address spaces? You know, how basically multiplex all these address spaces across a single physical memory. And the most common approach and a very flexible approach is to use page tables. And the idea is, and this is a hardware support. So this is implemented in hardware by the processor or by a unit called the memory management unit. And so the picture that you sort of should have in your head is, you know, yeah, the CPU that executes instructions, you know, like whatever our, you know, our store instruction that was, you know, putting $7 into A0 indirect. So it executes those kind of instructions. And, you know, when it executes one of the store instruction, load instruction, or whatever, anything that actually has an address, that address, we're going to think about it as a virtual address. So it's not a physical address, it's a virtual address. And so, for example, the value in A0 that we're using here, say that's 1000, OX, 1000, that is a virtual address. And that virtual address is basically routed through something what's called the memory management unit. And the memory management unit translates it into a physical address. And that physical address then, is actually used to, index into memory and load whatever value or store whatever value needs to be written there. And so the CPU, from the CPU's point of view, it always issues every instruction that it issues once the MMU is enabled are virtual addresses. And to translate these virtual addresses to physical addresses, basically the MMU has a table. And virtual address on one side, physical address on one side, on the other side. And for example, here is our entry for 1000, and maybe that maps to whatever OX, whatever. I'm just making something up with like some big value, somewhere in physical memory. And so this mapping between virtual and physical is quite flexible. So on one side we have the virtual address, on the other side of the physical addresses. Typically, this mapping itself is also stored in memory. And so the CPU has some register that basically points to, that contains the physical address of where the page table is stored. So somewhere in basically the page table or this map is somewhere stored in physical memory. Let's say, whatever, address 10. And basically this register, which is called on the RISC-V SATP, stores the address 10. And so that the CPU can tell the memory management unit where to find, basically the map to actually translate virtual to physical addresses. And then the basic idea is to give every application its own map. So, CAD is going to have its map. Oops. So every map, its own. Oops. Yeah. Vivek, go ahead.
So the MMU, you said it doesn't necessarily store the mapping. So does it just do the translation? Like it will read the memory and do the translation, but not necessarily store the mappings.
That's exactly the right picture that you should have in your head. And with every map, okay, so the map itself is stored in memory. The MMU just basically walks or looks up into the map. And we'll see in a second that this map is slightly more complicated than I was just drawing here. So every app has its own map, right? And that map basically defines its address space. And so when the CPU or when the operating system switches the CPU from one process or from one application to another application, it also switches the content of this SATP register to store the root of the map of the appropriate process. And so in that way, basically, multiple applications can run on the CPU. Every time we switch from one application to the next application, we also switch the SATP register to point to the appropriate map for that application. And in that way, basically, the virtual addresses for CAD are translated differently than the virtual addresses for the shell because each one of them has their own map. That make sense? Okay. So the way this is sort of the basic plan, and the way I've drawn or explained it so far is pretty naive and unreasonable. Yeah, Vivek, go ahead.
I'm sorry. So you said the SATP register gets modified for the process. I am guessing the value of for the SATP register for each process is stored by the kernel.
Yes. Yes, the kernel is writing the SATP register. In fact, writing or reading or particularly writing the SATP register is a privileged instruction. So a user application cannot just update the page map register and say like, I want to run with this page map now, because that would violate isolation. right? So it's only the kernel, only a code in kernel mode can actually update it.
I see.
Okay, so as I said, this picture is pretty naive. You know, one thing, I haven't really said anything about how this actually map works. You know, the way I've sort of drawn out seems to indicate that, you know, basically for every virtual address, you have an entry in the map. And if you do that, how big would the map be on RISC-V? Anybody? How many addresses are there on the RISC-V in principle, or how many addresses could a register store? Registers are 64-bit wide, so how many addresses? Anybody? I know I'm insulting your intelligence by asking these questions, but
We have some answers in the chat, like 2 to the 64.
so yeah, I didn't see the chat. Sorry. Yeah, 2 to the 64. Let's see if I can actually pop up the chat so I can see it. Yeah, 2 to the 64. Thank you. Correct. So this table would be gigantic. In fact, all memory would be consumed by just having that table. So that seems unreasonable. And so, in fact, that's not how things work. In fact, I'm going to go in 2 steps to actually how it actually works in the RISC-V. So step 1 is, don't play the game per address, but do it per page. So you translate a page at a time, and the page on the RISC-V is 4 kilobytes, and which is 404,096 bytes. And this is pretty common. Almost all processors, use roughly a page size of 4 kilobytes or support a page size of 4 kilobytes. And so now again, translation works slightly differently. So if here we have our virtual address, and basically we split it in 2 pieces: an index and an offset. And so the offset is basically the byte within the page. And so when we do, when the MMU does the translation, it takes the index, indexes into the map. That gives you, some physical page number, in memory. And that physical page number, okay, that points to some, physical page of 4,096 bytes. And then the offset part basically indexes into that physical page. So, for example, if the offset is, 12, then, the 12th entry of that page is actually used. And a lot of you people, a lot of you answered this mentioned this in response to the question that there's always some scheme of like taking an offset and adding that to the base of the page to obtain the actual physical memory location where a value is stored or where a value will be loaded to. And one of the interesting things about the RISC-V is, and this is in response to some question that somebody asked earlier, the physical or the virtual addresses are 64 bits, which makes totally sense, correct? Because the RISC-V is 64-bit register. But in fact, on the RISC-V processor that we're using, not all of the 64 bits are actually used. Namely, the top 25 are actually not used at all. And so that limits the size of a virtual address, right? That limits the size of a virtual address space to 2 to the power 39, which is roughly 512 gigabyte. And so, of course, later versions of the processor might support bigger address spaces if that isn't necessary, and that could then be done. And so, for example, some of those 25 bits that are basically unused, could be used to build bigger virtual address spaces. And so in the index, in that we have 39 bits left, as the virtual address, 27 bits are indexed, and we'll see in a second why they're 27 are indexed, and then the 12 are offset, and there have to be 12, correct? Because 2 to the power 12 is 4,096. All right, so that's virtual addresses. On the RISC-V, physical addresses, as you can see here, are actually 56 bits wide. So the physical memory, can be bigger than a single virtual address space, but it's limited to 2 to the power of the 56. And most boards probably, they don't support 2 to the power of 56 physical memory because there's a gigantic amount of physical memory. But in principle, a board could, if you could manufacture it, support 2 to the power of 56 of physical memory. And so in this scheme, then if you have 56 bits for the physical address, 44 are basically the physical page number, the PPN, and 12 again are the offset that are inherited directly from the virtual address. Does that all make sense? So I'm going to stop for a second here, so you collect your thoughts. The other point I wanted to make here is that this material is important. So just ask questions. The details matter, and it will be a large part of, you really need to understand all this stuff to be able to basically do the next lab, the page table lab. Yeah, Amir, go ahead, please.
If you could go back one slide,
Yeah.
The screen is unclear.
Which one? The page table slide?
Yeah.
This one?
No, the most recent one. But it also doesn't really matter.
Okay.
Yeah, this is perfect. Thank you. So I'm wondering, this 4096 byte range, which we've called a page,
Yep.
is that assigned as a continuous chunk in memory?
Yes, there's a continuous physical, continuous range of 4096 bytes in memory.
I see. And then
So you always map at a granularity of 4096 bytes.
Okay, and then 12, the offset, like 2 to the 12 is 4096, so that's sufficient to cover each of the chunks?
Yeah,
okay.
Each byte
and
in
where,
the page. Right.
And where does the 56 come from in the diagram? I could follow up until then, but I didn't get where that came from.
The designers cook it up. So the hardware designers decide how big, a physical address is, basically for whatever board they want to design. And so the RISC-V designers decided that 56-bit physical addresses were a good idea. And presumably the way they come up with these numbers is they look at technology trends and say like, well, we want to be able for the next sort of 5 years, we don't want to predict that physical memory will be ever bigger than 2 to the power of 56. And probably they're thinking it won't be bigger than something much smaller, but then give them some leeway, in case their prediction is wrong, they pick a slightly bigger number. Does that make sense?
I see. Yeah, thanks.
Yeah, a lot of people ask about this. Anybody else who raised their hand? I think there's a bunch of people asking questions, and unfortunately my Zoom doesn't show it's more than 2 people raise hands. It's just multiple people are raising their hand. So please jump in if you have a question. Okay, if not.
I have a question.
Yeah, go ahead.
So if the virtual memory is up to 2 to the power of 27 and the physical memory is up to the power 2 to the 56, right? Mm-hmm. So we could have, like we could have multiple processes that could exhaust all their virtual memories without using up all the physical memory, right?
That's correct. Yeah. That's absolutely correct. Okay.
I have a question too.
Yeah, go ahead.
So this 56 for the physical address, is that the number of possible memory locations? I don't think it's the number of bits, right? Because this is a 64-bit machine. That 56 could go up to 64, but they just chose it to have just 56.
That's correct. That's correct. And one way to think about it, then they only have to run 56 wires on the board as opposed to 64.
I see. I see.
Okay.
I also have a question.
Yeah.
So kind of, could you go back one slide maybe?
Yep.
So from the CPU, we go through the MMU and then to the memory.
Yeah.
But where here is the distinction for different processes? Because like each process, like process, like the shell process, has something at address like 0x1000, and then the ls process also has something at address 0x1000. So we need to translate those to different physical. So yeah,
the SATP register contains the address of which map to use. So ls runs with its own map, cat runs with its own map.
okay, so each process will have its completely own map.
Yep.
Makes sense. Thank you.
And in fact, there's a great leeway to the next point. So if every process has its own map, how big is this map, like that I've drawn here? Well, that map is 2 to the power of 27 entries, correct? And that's pretty big. And that would fill physical memory reasonably quickly if every process exactly had a complete, populated map. Right? And it's gigantic, it means that every process is very big. And so in fact, this is not the way the hardware actually stores page tables. You can think about it conceptually as an array, going from 0 to 2 to the power of 27, but actually is not what happens in practice. In practice, it's a multi-level structure. And here's actually the real RISC-V page table structure and what the hardware implements. And so what happens with the 27 bits that we saw earlier, the index, it's actually split in 3 9-bit numbers. And the top 9 bits are used to index into the top level page table directory, as they're called. And so in one directory, one of these guys, is 496 bytes, 4096 bytes, just like a page size. A PTE entry, one of these entries in the thing, is 64 bytes, 64 bits, sorry, like the register with, so 8 bytes. And so that's going to mean that if you do 496 divided by 8, means there are 512 entries in one of those directory pages. So basically what happens is the SATP points to the top root directory. We take the top level 9 bits, index into the page directory, and that gives us a new physical page number. And that physical page number is the page directory for the next level. So then we use the next level index to index into that page directory, and then, and so forth. We elect the final one, we get the bottom level page directory, and that basically gives us the entry that maps the virtual address to a physical address. So in some sense, it's very similar to what I showed you in the previous slide, except, basically the index happens in 3 steps instead of 1 step. And this is an advantage. The main advantage of this scheme is that then if large parts of the address space are not being used, you don't have to have any page table entries for them. And so for example, let's say you have an address space that has only one page, like the bottom page, so 4096. And no other pages are in the address space. So only the addresses 0 to 4096 are actually mapped. How many page table entry or page table directors do you need to map that particular page? Well, you need 1 at the top, correct? And you need basically value in that entry for 0. The top level 9 bits, of the 0 are 0. So you need an entry for 0. So that means you need 1 middle level entry, that basically corresponds to the next, 9 0 bits, and then 1 entry for the next 9 0 bits. And so basically we get away with 3 page directories. And in our previous scheme on the previous slide, correct, we had 2 to the power of 27 entries. And now we basically have to have 3 times whatever, 512 entries, and we're done. And that's the main reason why the actual hardware has this sort of hierarchical or multi-level tree scheme. Any questions about this? Because it's pretty important. Samir, go ahead.
So my question is, since the PPN number from each page table is 44 bits, and the second, say the middle table resides on the virtual memory, where do we get the missing 12 bits from?
Oh, the final 12 bits. Okay, so good. So you're saying these 44, correct?
Yes.
What is going on with that? Well, all page directories are page aligned, and so they're basically their physical page number is 44 plus the 12 0 bits. And so what actually happens if we look at these PTE entries, you know, they all have the same sort of form, correct? If you look at one of these guys, they're 44 bits, they're 12 bits zeros, so that gives us a 44 plus 12 is 56, so that gives us a physical address, correct? And so that means in these 64 bits, there's actually some bits left that are not being used. And in fact, the bottom 12 bits will basically, or the bottom 10 would definitely, you know, the bottom bits are not used at all. And in fact, the paging hardware stores there a bunch of flags that control the translation. And we'll talk about those flags in a second. But they're there to control the translation, and they're stored basically in the bottom 10 bits. And it also means, correct, that, you know, if you add these two up, that's 54 bits. Basically, there's 10 bits left that are unused. And those 10 bits are, again, you know, for future growth. So at some point, we might have a new type of RISC-V processor that will have a slightly different structure page tables, and it might actually have bigger than 44 bits for the physical page number. Okay.
Thank you.
And in fact, you know, you can see it here. Like if you look at a single entry, correct, that's drawn here. You know, there are basically 10 bits left that are not being used. Okay, so let's look at the flags for a second because that's sort of important. So every translation in the bottom 10 bits, there are a bunch of flags stored, and the first flag is valid. If the valid bit is set, that means this is a valid PTE, and you can use it for translation. And so for my little example that I used here with, you know, free page directories where only entry 0 is used, then only entry 0 will have the valid bit set, and none of the other 5 and 11 entries will not have the valid bit set. And that basically tells the MMU, well, you know, you don't have to chase down this PTE. This PTE just contains no valid information. Then R means, you know, you're allowed to read from that page. Write means you're allowed to write to that page. Execute means you're allowed to execute instructions from it. And user means, you know, this page is also accessible by a process running in user space. And then the other bits, you know, not that important. They will show up at some point, but those are sort of the 5 important bits. Does it all make sense? Yeah. Nithya, I'm probably mispronouncing your name. I apologize.
That's the right pronunciation. Thank you. I had a quick question about the 3 page tables.
Yeah.
So how are the addresses, or like the PPN values, combined to form the final physical address? I might have missed that.
Yeah, well, I may have not said it very explicitly. So the first PPN, correct, in the top of the page, the first PPN in the top level page directory contains the physical address of the next level down, right? And
okay.
That one contains the one next level down. And then in the final one, right, we still have our 44 bits, that contains then the actual physical address of the page that we're actually trying to translate to.
Ah, okay, that makes sense. Thank you.
Okay, and one interesting question, just as a side note, before, let me answer this, my own question before answering the 2 raised hands here. If you look back at this picture, why are the physical page numbers stored in these page directories? Why not a virtual address?
Because we need to look it up in memory, like look up the next directory in memory.
Yeah, right. We could not have, you know, our translation scheme depend on yet another translation scheme. You know, we get sort of a recursive infinite loop. So that just doesn't make sense. So that's exactly the right answer. It has to be a physical number. How about the SATP? What do you use the SATP? What does it store? Does it store a physical address or a virtual address?
Also physical, assuming that the first page directory is also memory, right?
Yep, yeah, exactly. So it has to be a physical number because we're actually trying to use it for translation. And so, the SATP needs to know what the physical page number is of the root of the page directory. Okay, there were two other questions, or two people that raised their hands. Could you repeat your question if
Sure.
it hasn't been answered yet?
So there's a hierarchy of 3 tables,
Yeah.
and each of them is indexed by a part of the virtual address,
Yes.
each 9 bits long. So I'm not sure I understand how chaining between them happens and what it's meant to accomplish. Like, shouldn't it be sufficient to just use those 3 9-bit addresses to index into each of them?
That's correct. So the top level 9 bits are used to index in the first top page level directory, the second in the next one, and the third in the third one. And
so maybe I'm just not understanding this correctly. So when a process requests a certain virtual address to be looked up, it loads into the SATP register, or the CPU does, and that gets the corresponding correct highest level page table.
yeah,
And then that page table will...
and we'll use then the top level 9 bits from the 27 to index into that page directory.
And then what is the result of that? Like, if the result is there's nothing there, does the MMU create a page table?
No, the MMU basically tells the operating system, or tells the processor, sorry, I couldn't translate that address. And basically it turns into a page fault, which we'll talk about a little bit later. But you just can't not translate the address, or it doesn't translate it. It's like, you can't divide by 0. If you try to do that, the processor just refuses to do it.
I see. Okay.
Brandon, or was that you, Brandon?
Yep. So I just wanted to make sure I understand how, I think maybe we covered it, but I want to understand how the kind of intermediate page tables, how we calculate the physical address of those. So is it correct that, say if we were trying to find a second level page table's physical address, we would take the PPN from the first level page table, that's 44 bits, and then we add the 12-bit offset from the original virtual address to get the full 56-bit physical address?
We don't add the offset from the virtual address. We just take 12 0 bits. So we take the PPN, that's 44 bits.
Okay.
We do 12 0 bits in the bottom, and that gives us a 56-bit physical address, and that's where the next page directory is. And this requires that basically every page directory is page aligned.
I see. Okay, that makes sense.
So these are all great questions, and these are all things you're going to be struggling with in the page table lab. So it's very good to ask them right now. Okay, let me see. Yes. Okay, let me hold on for a second. Collect my thoughts. Let's see where I am. Good. Okay, one one other thing that I want to mention, because you will see that, is that if we think about this, the scheme that I just showed, correct? What really seems to be going on is that when we load or store a value to memory, or the processor loads or stores a value to memory, we basically have to do 3 memory lookups, right? One in the top level page directory, one in the intermediate page directory, and then one in the bottom level page directory. So it looks like that, any memory reference to a virtual address basically requires 3 memory reads. And so that seems expensive. And so what happens in practice, where almost every processor does this, it has a cache sitting on the side that contains recently used translations. And this is called the translation leukocyte buffer. And you'll see that term quite often. It's called the TLB. Basically, it's nothing else than a cache of page table entries, PT entries. So when the processor has, the first time the processor looks up a virtual address, walks this, the hardware walks this the 3-level page tables, it will come out with, the final physical page, or the final PPN for that particular virtual address. And then basically the TLB stores .vn, VAPN or PA mapping on the site. And so then when the next time you refer to that particular virtual address, I can just look at straight up in the TLB and the TLB will respond instead of having to do the page table walk. Yep, I'm here.
So is it the TLB maps virtual addresses to the physical address of the page that the virtual address, along with the offset,
Yep.
maps to, right?
Yep.
Wouldn't it be more efficient to like cache at the page table level?
Okay, so let me take a step back here. There's many ways of implementing the TLB. The most important thing that you need to know is that there is a TLB. And the exact details of actually how the TLB is implemented is sort of, not a topic that we're going to talk about in a great amount of detail. In fact, not at all. And so this is really something that sort of sits inside of the processor and is mostly hidden from the operating system. The operating system doesn't really know how the TLB operates. The reason you need to know that the TLB exists is that if you switch page tables, then typically the operating system needs to tell the processor that it's switching page tables and the TLB needs to be flushed. Because basically you can't use stale entries, right? If you switch to a new page table, the entries in the TLB may not be valid anymore. And so they need to be removed because otherwise, the translation would be incorrect. And so the operating system is typically aware that there is a TLB, only basically to tell the hardware once in a while saying like, okay, well, don't use them anymore because I'm going to switch page tables. And in fact, on the RISC-V, the instruction to flush the TLB is called sfence_VMA. And that will actually flush the TLB. Vivek.
So I have a question, like not regarding TLB, but that brought kind of this question. The three-level support, the three-level paging that we have, is it implemented by the operating system or the hardware itself?
It's implemented by the hardware. So, this all happens in hardware. The MMU is a block of hardware, not in the operating system. We'll see in a second when we look at XV6, that XV6 has a function that models the page table walk because once in a while, SV6 basically has to do what the hardware does. And so it also does have a function called walk that basically does exactly the same thing, but in software.
So, can I ask a question?
Yeah, go ahead.
So, where in this scheme does the processor cache fit? Does it happen before the address translation or after? Because
okay, let me let's switch back a little bit. Let me see. Okay, here's your MMU. The way to think about it is that all this stuff, this whole block is inside of the processor silicon. So there's a RISC-V chip, and inside of it is the CPU. In fact, there are multiple CPU, correct? There are 4 cores, and there's an MMU. And you can think about that either on the CPU side, there's a TLB. Okay.
that makes sense. But I guess my question was about the cache in terms of not the TLB, but just the normal cache, because sometimes we don't actually go all the way to access the memory.
Yeah, good point. So I showed the schema last week, correct, or Monday of the RISC-V processor. It has an L1 cache, it has an L2 cache. Some caches are indexed by physical address, and some caches are indexed by virtual address. So the caches that are indexed by virtual address sit before the MMU, and caches that are indexed by physical address sit after the MMU. Does that make sense?
Oh, can I also ask a question?
Yeah.
My question is, you said that the TLB, it walks, so to put stuff into TLB, the hardware walks through the page tables.
Yeah.
Why do we write walk function if hardware can do that?
Very good question. one reason, again, there's a couple of reasons why we do it, or why XV6 needs it. One is when it actually sets up the initial page tables. It needs to program the three levels, and so it needs to basically emulate the three levels. Another example that you actually sort of ran into or are running into in the syscall lab is that when you copy, in XV6, the kernel has its own page table, and every user address space has its own page table. But once in a while, for example, in sysinfo, like the pointer to the sysinfo struct, that lives in user space, the kernel needs to be translated to an address that it can use to read and write it. And so, for example, if you're looking copy in or copy out, basically the kernel translates the user virtual address using the user page table to get out a physical address that kernel then to get an address out that actually then the kernel can use to read and write that memory. So there's a bunch of places where this shows up, and I'll talk about it hopefully in whatever 10 minutes or 15 minutes.
I have a question. Why doesn't the hardware like expose that walk function so we don't have to write our own and like potentially have bugs in it? Why isn't there like a maybe a privileged instruction that you can pass a virtual address and it'll give back the physical address?
Well, this is just store it to the virtual address and you get back and we'll do it right for you. So we'll see later on in the next lab, the page table lab. In fact, this is exactly what you'll be doing. You'll actually set up the page table slightly differently so that you can avoid the walk in copy in and copy in string. I think this will become clear in a second that when we talk about, look at the XV6, okay? Okay, good. One more sort of, basically before jumping into the XV6, I want to sort of make one point. One way to think about, page tables, a popular way to phrase this, is the page tables provide a level of indirection. And so basically this indirection grid, what I'm talking about, this mapping from virtual address to physical address. And this mapping is completely under the control of the operating system. As we've seen, in the last couple of slides that we talked. And that means that the operating system, because it has so much control over it, has control over the complete control of that translation, it can do all kinds of interesting tricks. And so, for example, like one trick, we talked a little bit about this, like if a page table entry is invalid, it will really return a page, the hardware will raise a page fault. In response to that page fault, the operating system could update the page tables and then maybe restart the instruction. And so there's all kinds of things that they can do at runtime by manipulating the page tables. And we're not going to talk about that today, but in 2 weeks, we'll have a lecture exactly sort of about this topic, about what cool things can you do once you have page tables and page faults. But it's important to keep in mind that this is an incredibly powerful mechanism that will provide the operating system with a tremendous amount of flexibility. And this is one reason why page tables are so popular. Okay, so what I want to do next is actually talk about XV6 and sort of see how this all plays out in XV6. And so the first thing I'm going to do is I'm going to look at the kernel page layout, if you will. And the mapping is on this slide. So here's the virtual address space. Of the kernel. And here is actually the physical memory. So this is what basically, whatever, you can think about this as DRAM. And in fact, it is not, let me take that back immediately. One part is DRAM, and one part is actually I/O devices. And so to sort of maybe I'm going to talk about the right side of the slide a little bit first, and then I'll talk about the left side in a second. So the left side of the slide is completely determined by the hardware. And so the hardware designers basically determine the layout of that thing. And as you saw before last week, when the kernel starts, it starts at this address 0x880. And that's just determined by the hardware designers. And to be more explicit, so if you look at the board, this is the same picture of the board that I showed on Monday, but it's hopefully a little bit better picture and it's easier to see. Here's our RISC-V processor. And we now know, correct, that in the RISC-V processor, there are 4 cores, but there's also an MMU, and there's also a TLB or multiple TLB. Every core has its own MMU, and every core has its own TLB. And here are the DRAM chips. And so basically, the designers of the board have decided that when after the translation from virtual to physical address, basically physical addresses that's starting at 08, a lot of zeros, actually go to the DRAM chips. Addresses below 088 may go to different I/O devices. And so the platform decides, basically, the designers of this board have decided exactly what the physical layout. And in fact, you can look that up, the physical layout, if you want to. Just let me show you that. So here's the same manual that I showed you on Monday. And if you go to, actually, escape. You go to page 31, I believe. Here is the page. And if you go down, it says, what is the memory? It will spell out what the memory map is of the board. And it will say, like, at address 00 is reserved, nothing is there. If you go scroll down in this memory map, you'll see some information about all the different things that are mapped. For example, the Ethernet board is mapped at 0x1, 0x something. If you go further down, oops, that was too much down. Here you see the entry for 0x8000, correct? And that actually is DDR memory, the off-chip volatile memory. And so those are the DRAM chips that I just showed you on the previous slide. And so it's just good to keep in your head, correct? Even though we're talking to QEMU and you're all going to see software, in the end, everything is determined by the actual board. Okay, so go back to my slides. So let's look at the layout. Yeah, Noah, go ahead.
Yeah, when you say that this layout is determined by the hardware, do you specifically mean like the CPU itself, or the board on which the CPU resides?
The board in which the CPU resides, correct? Because the board, the CPU is that gray thing in the middle, that square thing saying whatever RISC-V. The DRAM chips are sitting off the processor, correct? And it's the board designers who put the chip, the DRAM, the many I/O devices all together.
Got it. Thank you.
A large part, correct, of an operating system is actually, the CPU is one part, but the I/O devices are at least as important, right? And so when you're writing an operating system, you both have to deal with the CPU as well as, with the I/O devices. And you want to send a packet over the internet. Well, somebody has to take all, the network drive or the NIC card to actually do that, and that's the operating system. So going back to the right side of this picture, correct, which is the physical address layout, we see basically that the bottom was unused, as I showed you on that document. It turns out that 0x100, that physical address, that's where the boot ROM is. So when you turn on that board, the first thing that happens is actually code in the boot ROM runs. And when the boot ROM is done, it actually will jump to this 0x000, and it's the job of the operating system to make sure that there's some data there. And then there's a bunch of other devices that we'll talk about. There's an interrupt controller. We'll talk about it next week. There's a Clint, another part of the interrupt story that we'll talk about next week. So basically, multiple devices can generate interrupts. There needs to be a plan to route those interrupts to the appropriate request level, and that's all implemented by those interrupt controllers. And let me just finish for a second, this slide before answering the question. Then there's a UART. That was the device. That was actually the thing that actually the device that actually UART device that actually interacts with the console and the display, and then there's the disk, and that's the device. There's where the device sits that actually interacts with the disk. And so when you write to a location to address, let's say 0x200, then that physical address corresponds to the client. And so when you do store instruction or load instruction, you're reading and writing to the chip that implements the client. And we'll see later what that exactly means. But basically, you can think about this as interacting directly with the device and not reading and writing physical memory. Yeah, there was a question.
So just trying to make sure the addresses below 0x800, they don't really exist in DRAM.
That's correct.
If when we mention those addresses, we directly go to the other hardwares.
Yeah, yeah. So like if you just go back to this picture, anything above 0x10, correct? That's these DRAM chips. And I can't point you to the client, but like for example, here's the Ethernet. And so that sits a particular physical address, and we can write, with load and store instructions. This is called memory mapped IO. We can do with load and store instructions. We can program the Ethernet controller.
I also have a question. Why is this big chunk at the top says unused? Why is it not used?
Oh, okay. So remember, not every machine, so there's 2 to the power 56 bytes of physical address space. But you don't have to, plug in that much memory into the board if you don't want to. And so some parts of it may be unused, depending on how much, DRAM chips are sitting on the board. In fact, like in XV6, I think, limit ourselves to 128 megabytes and no more.
So when load or store instruction goes out of the CPU, does that go, like, where does it get routed to the correct IO? Like already from the CPU? So kind of like if the CPU, before it sends it out, it says, okay, if it's lower than 0x8 and all the zeros, then I'm going to send it to like the correct IO device. And then otherwise I'm going to send it to the memory, like the DRAM chip.
Yeah, you can think about it as a demultiplexer sitting on the inside of the RISC-V, blob.
Oh, so it's inside of that block.
Yep.
Okay.
There's a memory controller and does the routing. Good. Very important to have that sort of all clear in your head. Okay? So now I want to switch to the right side of this picture. And this is basically what XV6 sets up to the virtual address space that XV6 sets up. So when the machine boots, there's no paging enabled yet. XV6 sets up the first, page tables, the first virtual address space, and that's actually the virtual address space that the kernel uses. And we'll look at it in a second at the code. And this is the layout. And it turns out, because we want to keep XV6 as simple as possible and so easy for you to understand, the mapping from virtual to physical is mostly an identity mapping. So basically what that means is that the virtual address 0x200 maps to physical address 0x2000. So the kernel will set up the page tables exactly in that way. And so that means basically that, sort of all virtual addresses below phys top, which is the top of physical memory, are identical to the physical addresses that are actually being used on the right side. And so this is like why all the arrows are straight, because it's an identity mapping. Okay? There's small changes to this. There are 2 important things to mention. Amir, hold on a second while I try to first mention the 2 important things to mention. First of all, there's some pages, some mappings very high up in memory. There's some pages very high up in memory. For example, the stack, the kernel stack actually is also mapped high up in memory. And the reason it's high up in memory is because we have a guard page below it that is not mapped. So the PTE entry below the kernel stack of one of the kernel stacks does not have its valid bit set. And so if the kernel runs off its stack, it will result in a page fault, which is better than basically scribbling over some other memory that the kernel has. You get an immediate panic and you know that something's bad with the stack. And of course, we don't want to waste physical memory. And so we do that by basically putting the stack high and a guard page, an empty guard PTE entry below it. And the guard PTE page doesn't really consume any physical memory, right? It's sitting high up in the virtual address space, so nothing is being consumed. But that means that this K-stack page, for example, is mapped twice. It's mapped at a high address, and it's mapped directly by one of the addresses that below fist top. And so you can do, this is one example of all the sort of cool things you can do with page tables. You can map a physical address twice. You cannot map a physical address. It can be one-to-one mapping, one-to-many mapping, many-to-one mapping. All that kind of stuff is possible. X86 doesn't really use many of them, but there's a couple places we use those tricks. And the stack and the guard page is one example of one of the cool tricks that X86 uses, mostly to track down bugs. The second thing I wanted to mention is that the permissions. So for example, the kernel text, the pages for the kernel text are mapped read and X, meaning you can read it and execute it, but you cannot write the kernel text. And again, this is basically to avoid bugs so that we catch them early. Kernel data, of course, needs to be able to be written to, and so it is mapped read-write, but you cannot execute out of kernel data pages instructions. So the X bit is not set. Does that all make sense? I skipped one or two questions, so if these questions are still not answered, please ask them.
We have a question in the chat.
Yeah.
Do we have multiple kernel stacks for different processes? Like, will we have n K stacks for n processes?
Answer is yes. So every user process has a corresponding kernel stack. And we'll see that in a little bit later. Okay. Okay, so let me, Samir, go ahead.
So would the virtual memory of another application map to somewhere in the physical memory in the unused space, or?
Yes, very good point. So there's a bunch of physical memory, correct? Here's free memory, and that's free memory here too, correct? We use that, or X86 uses that free memory to basically store pages of page tables of user processes, as well as the text and data of user level processes. And if we run many user level processes, at some point we'll run out of free memory, and then basically fork or exec will return an error.
But that means that the virtual space for processes are much smaller than the virtual space for the kernel, right?
Well, the virtual space is the same size in principle, but it will be less populated. Then let's go look at some code, and I think that all the stuff becomes a little bit more clear.
Just one small thing so given that a lot of each process has a big part of the memory mapped to the same location, is that optimized by consolidating that into one place, that mapping, or no?
You could. X86 does not do that. But one of the challenge exercises in the page table app is to actually implement that.
I see.
And a real operating system would do that. Yeah,
Makes sense.
Very good question. And I think you get a sense of what all kinds of things are possible once you have page tables. Okay, so let's do the usual thing. Boot X86 again, and again, QEMU is just basically implementing the board. And let's, oops. So last time we looked at how the booting happens, correct? And then we got to main, and then basically one of the things that the kernel, when one of the functions is called kvm init, and that actually sets up the address space for the kernel. And so we saw in the picture or in the previous slide what that looks like, and here we're going to see in code how it actually is being set up. And why? Hold on, something's not going as I want it to. Am I in the right directories? Hold on a second here while I'm trying to sort out my problems. That is good. And in the right directories, yeah, okay, GDB. And I'll set a breakpoint in main just to make sure. Good. And then I'll set a breakpoint at kvm init. Actually, I can just step to it now. Next, console init, printf init. We saw that before. Physical memory allocator. And now something happens that I'm not expecting. What is going on? Of course, I ran this right before lecture. Oh, here, that's what's going on. That actually is printing. Okay. Interesting. Okay, one more time, see if I can get lucky. More, let's. Continue, and hopefully it will get there. I'm going to wait a little bit. Okay, great. We're at the kvm init. So basically, we're now at this function here on the right side in the Emacs buffer. You can see it. I think I modified the function slightly. I hope I did. I think I did. Well, we'll see. And what we're going to do is we're going to step into that function. Do me the layout split. It's easier to see. And actually, the first thing that you can see is actually the kernel actually allocates a physical page for the top level page directory. And then it zeroes it out so that all the PTE entries are 0. And then basically it starts mapping in every device, IO device, one by one. And so, for example, the UART0, it basically starts maps that into the kernel address space. And so we can look at a file called memlayout. This basically translates that page 31 that I showed you from the document into a bunch of constants that we're using. And so, for example, here it says what the address of UOX1000 is, or what the UART is. And so, we can basically map it into the address space by calling this function kvm map, which I'll look in a second. And then in the first exercise of the page table app, you are asked to implement a function called vmprint. And I implemented it too, and we're going to step over it, and we'll see basically the page tables, the kernel page table as it is set up after that one call to kvm map. So I'm going to do that, and boom, and it prints out something. And so we're going to look at a little bit of the output here. So here's the page table. That is the physical address of the top level page directory. So the thing that actually sits in SATP or will sit in SATP. And then, we have entry 0 of the top level page directory has one PTE entry in it. And that contains the physical address for the middle level page table directory. The middle page table directory has one entry, namely 128, and that points to the bottom page table directory. And the bottom page table directory has the entry then for the physical page. And you can see indeed that the physical address, for that, the bottom level is OX1000 corresponding to UART0. Right? So basically, virtual address 1000 translates to physical address 11100. And we can sort of double check that this is indeed all legit, right? By let's take that address, that OX100L, and we're going to shift to 12. And that should be, that gives us the top level 27 bits. shifted 9. So I'm going to take OX100, 1000, 101 more, and we're going to shift it 9 and print that. And that is OX0. And actually, if we print OX0 as a decimal number, it's going to be 128. Okay? So we see actually sort of, it all sort of makes sense. We also see, I printed out the flags here, and, the bottom level has read, write, and valid, because valid is 1. Any questions about this? Okay, so the kernel basically proceeds, setting up the whole address space in this way. And so it calls kvm map, for virt.io, for the clint, for the click. It maps the kernel text, maps the kernel memory or kernel data, and then the trampoline page that we'll talk about next week. And so in fact, we can sort of single step through this and then see what the final page directory looks like. So next. Basically, we set the trampoline, and so now we're going to print the complete page table directory. And we see, basically a lot of PTEs actually being set up. And I'm not going to really talk about it in any detail, but basically it fills out the page directory to actually create that virtual mapping that we basically saw in the previous slide. In fact, what I want to do next is actually much more interesting. I want to go here actually. I guess I maybe already did this. We're 21. No, I'm 21. Okay, so single step in that. Okay, that's too bad. I got past it. But basically, actually, let me restart this. And I want to breakpoint at kvm init heart. And continue. Boom, I'm now here at kvm init heart, and you see here basically that we're writing the SATP register. So basically the kernel is going to enable the page table or the MMU to basically start using the page table that we just set up. And one interesting question, okay, so then I do a layout split again. So somewhere here, correct, is going to be, here's the instruction. And so once, so something really dramatic happens after executing this instruction. Let's say, I can't see the assembly instruction exactly, but there's this extent. Once this instruction is executed, what will happen with the next address that's being translated? Well, at the point that we execute this instruction, before executing this instruction, there's no page tables enabled yet, so no translation happens. But the next, and then the program counter is updated by 4, and then the next instruction is executed, and the program counter will be translated using the virtual page table memory. And so this is the way to think about this is a dramatic moment, because basically the whole address translation is starting to enable, and every address means maybe potentially something different. Right, because before we were running just like the physical addresses, then the page table handler set up, and whatever is in the mapping, that is now the new meaning of a virtual address. And this is how this works out. The fact that this actually works out is sort of remarkable, because like the next instruction, the next value is a virtual address and not a physical address. Right? The next instruction is going to be this whatever OX1110. And why does this work out? Well, the reason it works out is because the kernel is set up with an identity page mapping. So after we enable the virtual paging hardware, we actually, this translator will translate again to the same physical address. And so indeed, we'll actually end up, executing the right instruction, because that's actually exactly the instruction, the memory location that the virtual hardware is programmed for. So does this make sense? Again, one reason why programming with virtual memory is difficult is because once you execute one of these SATP instructions, you load a page table in the SATP register, your world completely changes. And every address is now translated with the page table that you set up. And so what happens if the page table is set up incorrectly? What might happen? Anybody who wants to say that, answer it, or answer it in the chat, either way.
You could override kernel data.
Yeah, you could overwrite kernel data. What else could happen? Yeah, page fault. You know, basically the mapping may be incorrect, and basically the address can't be translated at all, and so the kernel can, you know, the process hardware won't do it, and the kernel just stops, it panics. Does that make sense? So if you get a bug in your page tables, you know, you're going to see bizarre errors or crashes. And so one reason that, for example, the next lab, the page table lab that we'll hand out or release tonight is going to be hard, is because those kind of bugs will show up. And you're going to be not careful enough, or you haven't fully internalized some aspect yet, and you're basically going to get a kernel crash, and you're going to have a hard time, where, you know, it will take a little bit of time and energy and detective work to basically track down why that happened. And that's just part of like programming virtual memory, because it's such a powerful primitive. You know, if you get it wrong, you're also going to have powerful consequences. Yet, on the other hand, it's a great amount of fun. So I don't want to end on a negative note, but that will give you sort of a real understanding of actually what really virtual memory is and what it can do. Okay, I think I'm running out of time, so I'm going to stop here so that people have time to go to the next class or next activity. But if you have any questions left, you know, please hang on and ask them. And we'll see you on Monday. And good luck with finishing the Cisco lab.
Hi, I have a question about walk. So it says, and in the code, it returns the first table's PTE.
Yeah.
Is that right? But how does it work then? Like the other functions, wouldn't they expect the actual PTE, that like the physical address? Like,
yeah. So basically, this returns the PT entry in the page table, right? And the kernel can read and write page table entries. And so now you can stick values into the PTE. And so maybe I can draw a picture if that is helpful. Let's see. So basically we have a page directory. And, you know, this walk code, so the page directory has 512 PTEs in it. And here's 0, here's 5 and 11. And basically what the function does, it returns a pointer to one of these PTEs. And so that's just a virtual address, and it just points to that particular PTE. And now the kernel can, you know, manipulate that PTE by like whatever, writing values to it, like some physical address, maybe with some permissions ORed into it for the bottom 10 bits. And then that basically updates the page table directory. And then later on, when you load that into SATP, now that change will go into effect. Does that make sense?
Yeah, that makes sense. I guess I was just confused, like, why does it do the work of going all the way to the third page table and then only return the first PTE?
No, it returns actually the bottom one. Actually, well, let me be careful. If you notice, it goes through the n levels. So it starts at level 2, and then it goes to level 1, and then it goes to level 0. If the alloc bit is set, and level doesn't exist, it will create the intermediate page table directory and zero it out, and then keep going in the loop. So if alloc is set, you always end up on the bottom PTE. If alloc is not set, you stop at the first PTE that doesn't have a value.
Okay, that makes sense. So this is the last one, the actual one that's gonna have, okay, the physical. Okay, thank you.
Any other questions?
So I have a question. Uh, Basically, everything made sense until we mapped the virtual addresses of the kernel to the physical addresses.
Yep.
So my understanding is that each process will have its own page table, which is also a 3-level tree, which
Yep.
maps its virtual addresses to physical addresses.
Yep.
But then when we map the kernel virtual addresses to physical addresses, I don't think we accounted for the actual tree of the virtual addresses of the kernel, or where other processes will have their virtual addresses and virtual addresses. Like the page table trees and whatever the
Yeah.
page table tree points at in the physical memory.
Yeah, so here's back. So this is a slide with the kernel address space, the virtual kernel address space. And so when the kernel allocates a proc and the page tables for that particular process, they're going to be allocated out of memory here. Memory that's not being in use yet. And the kernel is going to program, we'll probably allocate a couple pages for the page table of the user level process, and we'll fill in the PTEs. And then some point when the kernel runs that process, it will load the root physical address for those pages that it allocated for that page table, or basically for the page table that it built into the SATP register. And at that point, the processor will run with the virtual address space that the kernel constructed for that particular process.
So the kernel give up some of its memory for processes, but then the virtual space in theory is as big for the process as the kernel.
Exactly.
But in reality, it's really not.
Yeah, for example, here's the picture with the layout of a virtual address space of a user level process. And again, it goes from 0 to max VA in the same way as the kernel address space does. And it just basically has its own set of page tables to map those, to do the translation that the kernel set up.
But we can't actually use all of the max VA virtual
No,
addresses.
we cannot, because we run out of memory.
Mm-hmm.
So many of the processes are much, much smaller, correct, than all of the virtual address space.
I see, thank you.
I've got a quick question.
Yeah.
Could you go back to the walk code?
Yeah, absolutely. It's one of my favorite functions.
So I guess, I think one thing I'm confused about is after you write to the SATP register, can the kernel even access physical addresses directly? So it looks like in the code that it's converting, like page table is being set to a physical address. But if SATP is set, won't that be interpreted as a virtual address?
Yeah. So let's look at whatever the hard in it. So there's a KVM, so built to the kernel address space. The kernel page table initially is a physical, is an address is translated to a physical address, and that's actually written into the SATP register. And at that point, we're running with the address space that we constructed like right before here in this KVM init. And KVM map is basically nothing else than calling walk for every address or every page in that range. And so what was your question?
I guess does walk still work the same way if you call it after SATP is set?
Yeah, why?
Yeah.
Why will it work out? The reason it will work out is because the kernel set up an identity mapping.
Okay. Right.
Very important. Very good question. Like a lot of things just happen to work out because actually the identity mapping is set up.
I see. Okay, I think that makes sense. Yeah. Thanks.
I have a quick question.
Yep.
Where are the SATP registers stored for all of the processes?
There's only one SATP per core, but in every proc structure,
Okay.
if you look in proc.h, there is a pointer to the page table here. Here we
Okay,
go.
that makes sense.
Yep.
And also, with regards to the three page tables, or like the three tables that can complete the full address and help you get a full address for given something, how is that better, I guess, than having one giant page table? I didn't really fully understand that.
Good. That's a great question. The reason is because in the free level page table, you can leave a lot of entries empty. So, for example, if you leave an entry in the top level page table directly empty, you don't have to create middle level page tables or bottom level page tables at all for those entries.
Okay.
And so like this means like a big swath of the whole virtual address space doesn't have to have any mappings at all.
Okay.
You don't have the table there. It just doesn't exist.
So you're basically allocating these chunks on demand as opposed to having the entire thing. Okay, that makes sense.
Yeah, you start out basically with three pages, namely one for the top level, one for the one intermediate, and one for A and one bottom level. And then as you go, you create more page table directories.
Okay, cool. Cool, thank you so much.
You're welcome. Any more questions?
Sorry, I have another one. It's really small, but in the VM.c on line 43.
Yep, hold on.
Or sorry, 40, line 40, yeah. It says that no, never mind, 43, my bad. It says physical stop minus UN64 etext, but wouldn't that go over the, I guess the memory that we shouldn't touch? I don't know if that makes sense, but wouldn't that go, I guess I don't understand, wouldn't that go over free memory?
No, I don't think so. So current base is 0x880000, correct? So that's the beginning of memory. And the kernel sits there, and basically this thing is a size, right? So etext is the last address of the kernel. Subtract kernel base, that basically gives you the size of the kernel in bytes. And I don't know how much it is, but it's like 60 or 90 pages or something like that. And so this maps is basically the text part of the kernel, and there's enough space, there's enough DRAM to map that, the kernel text. I'm not sure I'm answering your question, but.
Oh, I think I understand. I thought that etext starts somewhere else. Okay, I think I understand now. Thank you.
So etext is basically the last instruction, the address of the last instruction of the kernel.
Okay.